Hi there, my name is Luca Ferranti, and in this talk I will introduce geometric theorem prover.gel, a package for automated theorem proving in Euclidean geometry. First, I will give a short introduction to the topic, then I will use a running example to demo how to use the package, and finally I will give a short roadmap of further development. First, why do we care about Euclidean geometry in the first place? Well, most are familiar with the Elements, the work of Euclid, where he formalized axiomatically Euclidean geometry. And this is important for being one of the first axiomatic systems in the history of mathematics. And even today, Euclidean geometry is still fundamental, for example, in pedagogy, as it's, for example, for high school students, the first contact to the concept of proof and axiomatic system. Things get more exciting when Tarski in the 30s proved that Euclidean geometry is decidable, which means that in principle one should be able to write a computer program which can decide whether a given statement of Euclidean geometry is true or false. And during the years there have been several approaches to actually implement this kind of computer program. These approaches can mainly be divided into two types: algebraic methods, which are generally more powerful but don't produce a human-readable proof, and synthetic coordinate-free methods, which are less efficient but can produce human-readable proofs. In this talk, I will talk about the read-through method, which is the only method implemented in the package at the moment. It's an algebraic method, which means that converts the constraints to polynomials and does the proof by manipulating those polynomials. It has some limitations. For example, it can only prove theorems involving equalities, and the main drawback is that the proof is not human readable because it's a bunch of polynomials. In a nutshell, the steps of the algorithm are to first determine what points are free, what points are fully determined, what points are semi-free, assign coordinates to the points, transform the hypothesis to polynomials, triangulate the system, convert the thesis also to polynomial, compute the so-called pseudo divisions, and if the last pseudo remainder is 0, the theorem is proved. What does it mean? Let's use a running example to understand better. So let's consider this theorem called Apollonius circle theorem, which says that if I have a triangle ABC right on A, and I consider the midpoints of the sides and the projection of A to BC, these 4 points, M1, M2, M3, and H are on the same circle. How do we do this with geometric theorem prover.gel? We have this at HP macro, which allows us to write the statements, and these statements are parsed and converted to hypothesis object. The main philosophy of the package is that points are introduced by constraints. So when I write the C colon equal segment AB perpendicular segment AC, it means that I'm assigning a constraint to the point C. I'm constraining the point C by this constraint. Similar, M1 is constrained to be the midpoint of A and B. And for example, H is constrained to be the projection of A to the segment BC, and O is constrained to be the center of the circle through M1, M2, and 3. And after parsing, we get this result. So points A and B are free, point C is semi-free, and so it's constrained by this equation, but there are still infinitely many options for it, and M1, M2, and 3, and H, and O are dependent points. So they are fully determined by these constraints. Similar for the thesis, I want to prove that the 4 points are on the same circle. So this is the center of the circle passing through these 3 points, and I want to show that the 4th point is on the same circle. And similarly, this can be done with the at th macro, which will parse the statement into thesis object. To prove, we have the function prove, which takes hypothesis and thesis and generates the read-through proof. So first, it prints the assigned coordinates. So we see that A has been assigned to be the origin, B to be on the x-axis, because I have gauge freedom that I can fix. Also, we saw that B was a free point, and so it has this U variable. U is for free variables and X for dependent variables. So this is arbitrary. C was semi-free, so has 1 free variable and 1 dependent variable, and the other points were fully determined, so they have dependent variables. We see it's successful, so it can prove that the theorem is verified, and it prints these non-degeneracy conditions, which I will explain in a second. Now, let's see what happens under the hood. So, as I said, first we assign the coordinates, and then we convert the statement to polynomials. So each statement is converted to a polynomial, like this. Then we want to triangulate the system, which means that we want the first equation to only have x1, the second x1, x2, the third x1, x2, x3, and so on. And this is actually almost already in triangular form, but for example, if you look at the equations 8 and 9, equation 8 has both x8 and x9, but should only have variables up to x8. So we fix this by triangulizing the system, and this is the triangulized form. So we see now the 8th equation only has x8 and previous variables, and x9 is introduced in the 9th equation. After we have the triangulized system of hypotheses, we can compute the proof, which is based on successfully computing pseudo divisions. So this last polynomial here is the thesis. Then I take the pseudo remainder of these with the last hypothesis, and then I take the pseudo remainder of that with the second last hypothesis, and so on recursively. And if the last pseudo remainder is 0, then the theorem is verified. And the readful theorem method also creates non-degenerate conditions, which are extra assumptions that I need for the proof to be valid. So if I have a triangle, I want it to be a triangle. So I cannot have all the 3 points to be overlapping. And these are the non-degenerate conditions. So statements like point A, B are distinct, or they're not on the same line, or stuff like that. And well, the method actually can generate for us automatically these non-degenerate conditions, but unfortunately they are polynomials. But still, we can actually reason something. For example, if you look at the first, it says that U1 is non-zero. And if we look at this, if U1 were 0, A and B would be the same point. So this first equation says that A and B are distinct. And similarly, I can try to reason also for the other equations and give a geometrical meaning to these constraints. So the package is at early stages, and there's still a lot of room for improvement and new features and so on. One next step is this plotting. So I would like the package to automatically generate the plot, which I had, for example, in the slides from hypothesis and thesis, and hopefully this will arrive soon. Then another milestone is to implement this area method, which is a nice method because it gives human readable proofs. And the last goal, I think, would be nice to have a repository to collect formalized Euclidean geometry, sort of a library of Euclidean geometry. Thank you for listening, and if you have any questions, I would be happy to answer.